The observable universe is 93 billion light-years across. It contains an estimated 2 trillion galaxies. The Milky Way alone has between 100 and 400 billion stars. The Sun, one of those stars, is large enough that 1 million Earths would fit inside it. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. If you drove there at highway speed, the trip would take 54 million years. These numbers are not analogies, they are the actual numbers. The universe is genuinely, incomprehensibly enormous, and it was all created in a single event 13.8 billion years ago that started smaller than an atom. The Milky Way is so large that light takes 100,000 years to cross it. The nearest galaxy cluster, the Virgo cluster, is 65 million light-years away. The most distant object ever observed is a galaxy seen as it existed just 320 million years after the Big Bang, meaning its light has been traveling for 13.48 billion years to reach us. The universe does not have a meaningful edge in the direction we can look, because in every direction we eventually hit the limit of what light has had time to reach us from. This is all of astronomy, from nothing to everything, in 20 minutes. The universe began with the Big Bang. This term is slightly misleading. It was not an explosion of matter into empty space. It was the rapid expansion of space itself, carrying matter and energy along with it. There was no center. Every point in the universe was at the same point. Every point in the universe was at the same point. Every point expanded away from every other point simultaneously. The Big Bang happened everywhere at once, including where you are sitting right now. At the very beginning, the universe was extraordinarily hot and dense. In the first fractions of a second, the 4 fundamental forces may have been unified into a single force that immediately began separating. Within the first second, the universe was filled with a seething plasma of quarks, electrons, photons, and neutrinos, colliding continuously at temperatures of about 10 billion degrees. In the first 3 minutes, as the universe expanded and cooled enough, protons and neutrons combined to form the nuclei of the lightest elements. Hydrogen nuclei, single protons, formed first. Some hydrogen nuclei fused to form helium. Trace amounts of lithium formed. This process, called Big Bang nucleosynthesis, lasted only a few minutes before the universe cooled enough that fusion stopped. The ratio it produced, about 75% hydrogen and 25% helium by mass, matches exactly what astronomers measure in the oldest stars today. For the next 380,000 years, the universe remained too hot for electrons to attach to nuclei. It was opaque, a thick fog of charged particles scattering light in every direction, like trying to see through a wall of steam. Then the temperature dropped to about 3,000 degrees Celsius, and electrons and nuclei combined to form neutral atoms for the first time. The fog cleared. Light traveled freely for the first time in cosmic history. That light is still traveling today. We detect it as the cosmic microwave background radiation, a faint glow coming equally from every direction in the sky at a temperature of about 2.7 Kelvin. It is a photograph of the universe at 380,000 years old, and it matches theoretical predictions to extraordinary precision. The slight variations in temperature across the CMB, tiny fluctuations of 1 part in 100,000, represent the density variations that seeded all the structure in the universe. Every galaxy, every star, every planet, everything. The cosmic microwave background was first detected accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to calibrate a radio antenna and kept picking up an unexplained background hiss coming equally from every direction. They checked for pigeon droppings inside the antenna. The hiss remained, it was the afterglow of the Big Bang, and they received the Nobel Prize for accidentally discovering it. The CMB has since been mapped in extraordinary detail by satellites including COBE, 921AP, and Planck, and every measurement confirms the Big Bang model. After the CMB was emitted, the universe entered a period called the Cosmic Dark Ages. There were no stars yet, no galaxies, just clouds of hydrogen and helium gas slowly drifting through darkness, pulled by gravity toward the denser regions marked by those tiny CMB fluctuations. To give a sense of the scale involved, the observable universe is 93 billion light-years across, but light from the most distant objects we can see left those objects when they were only a few 100 million years old. We are looking back in time when we look out into space. Every telescope is a time machine. The James Webb Space Telescope, launched in December 2021, has observed galaxies forming less than 300 million years after the Big Bang, pushing back the edge of what we can directly observe. The first stars ignited somewhere between 100 and 300 million years after the Big Bang. These stars were nothing like the ones we see today. They formed from pure hydrogen and helium with no heavier elements, and they were enormous, estimated to be hundreds or even thousands of times the mass of the Sun. They burned fast and hot, living only a few million years before exploding as supernovae. Those explosions forged the first heavy elements, carbon, oxygen, nitrogen, iron, and scattered them into the surrounding gas clouds. This is where every atom in your body above hydrogen and helium came from. Carbon was fused in the cores of stars. Calcium in your bones was produced by a dying star. The iron in your blood was produced in a supernova. You are, in a completely literal sense, made of material that was once inside a star. The first supernovae injected enough energy into the surrounding gas to ionize the hydrogen fog that had formed during the Dark Ages, a process called reionization that was mostly complete by about 1 billion years after the Big Bang. The universe became transparent again, this time permanently, as gravity continued pulling gas and dark matter together over hundreds of millions of years. The first galaxies assembled. Early galaxies were smaller and more irregular than the large, structured spirals and ellipticals we see today. They merged, cannibalized each other, grew larger, and settled into more regular shapes over billions of years. The role of dark matter in all of this is enormous, even though we cannot see it. Dark matter makes up about 27% of the total mass energy content of the universe and interacts with normal matter only through gravity. It does not emit light, absorb light, or interacts electromagnetically. But because it was present in the early universe in large quantities, its gravitational influence shaped the distribution of matter at every scale. Without dark matter, the slight density variations in the early universe would not have had enough gravitational pull to collapse into the dense structures needed to form the first galaxies. The large-scale structure of the universe, the cosmic web of filaments, walls, and voids connecting galaxy clusters, matches exactly what simulations predict when dark matter is included. Galaxies are not isolated objects. They exist in clusters, bound together by gravity and dark matter, strung along the filaments of the cosmic web. Our galaxy is part of the Local Group, a collection of about 80 galaxies, spread across roughly 10 million light-years. The largest members are the Milky Way and the Andromeda Galaxy, which is currently approaching us at about 110 kilometers per second. In roughly 4.5 billion years, the Milky Way and Andromeda will merge into a single, larger elliptical galaxy. The night sky, if anyone is around to see it, will look nothing like it does today. The merger will be a slow gravitational dance over hundreds of millions of years. The stars are so far apart that very few will actually collide. We know dark matter exists because of its gravitational effects. Galaxies rotate faster than they should if they contained only the visible matter we can detect. Clusters of galaxies bend light from background objects by far more than their visible mass would allow. The Bullet Cluster, two galaxy clusters that collided roughly 150 million years ago, shows the hot gas from each cluster slowed and merged at the center as expected, while gravitational lensing reveals that most of the mass of each cluster kept moving, passing through the collision undisturbed. That mass is dark matter. Now let's talk about stars, which are where most of the interesting physics in galaxies actually happens. Stars are the engines of the universe. They convert hydrogen into helium, and in later stages, helium into heavier elements, releasing the energy that lights galaxies and forging the atoms that eventually end up in planets and people. Every element heavier than hydrogen and most helium was produced inside a star or in a stellar explosion. Astronomy and chemistry are not separate subjects at this scale. Stars are the factories that produce the periodic table. The Sun is a fairly average star by mass, though it is larger than about 85% of stars in the Milky Way, most of which are smaller, cooler red dwarf stars. Red dwarfs burn their fuel so slowly that the least massive ones have lifespans exceeding the current age of the universe. No red dwarf has ever died of old age. The universe is too young. A star forms when a cloud of gas and dust collapses under its own gravity. As it contracts, the center heats up. When the temperature reaches about 10 million degrees, hydrogen nuclei begin fusing into helium, releasing enormous amounts of energy. The outward pressure from this fusion balances the inward pull of gravity. The star has reached the main sequence where it will spend most of its life. The Sun has been on the main sequence for about 4.6 billion years and has roughly 5 billion years remaining. It fuses about 600 million tons of hydrogen into helium every second. The Sun is 1.4 million kilometers across. Light takes about 8 minutes to travel from its surface to Earth and roughly 100,000 years to diffuse from its core to its surface. The core, where fusion happens, is about 15 million degrees. What happens when the hydrogen runs out depends almost entirely on the star's mass. A star like the Sun, after exhausting its core hydrogen, will expand dramatically. The outer layers swell outward as the core contracts and heats further, eventually fusing helium into carbon and oxygen. The Sun will expand into a red giant large enough to engulf Mercury and Venus, and possibly Earth, in about 5 billion years. After that, it will shed its outer layers in a beautiful expanding shell called a planetary nebula, and the core will cool and shrink into a white dwarf, a dense, Earth-sized remnant of carbon and oxygen that will slowly radiate its heat into space over billions of years, eventually becoming a cold, dark object called a black dwarf. No black dwarfs exist yet. The universe is not old enough. More massive stars, and more dramatically, a star with 8 or more times the mass of the Sun burns much faster and lives far shorter. A star 20 times the mass of the Sun might live only 8 million years, a blink in cosmic terms. When its fuel runs out, the core collapses catastrophically in a fraction of a second, bouncing back in a supernova explosion powerful enough to briefly outshine an entire galaxy. If the remaining core has a mass between roughly 1.4 and 3 solar masses, it forms a neutron star, an object about 20 kilometers across with the density of an atomic nucleus, so dense that a teaspoon would weigh about 1 billion tons. If the core is more massive, nothing can stop the collapse, and it becomes a black hole. Neutron stars are among the strangest objects in the universe. A typical neutron star packs 1.4 solar masses into a sphere about 20 kilometers across. The gravity at its surface is roughly 200 billion times stronger than Earth's. Some neutron stars spin hundreds of times per second, emitting beams of radio waves as they rotate, detectable from Earth as precisely timed pulses. These are called pulsars, and they are so regular that they were briefly considered as potential signals from an extraterrestrial civilization when first discovered in 1967. The discoverer, Jocelyn Bell Burnell, initially labeled the signal LGM-1 for little green men. It was not. It was a pulsar. When 2 neutron stars orbit each other and eventually merge, they produce gravitational waves, ripples in space-time, detectable from Earth. In 2017, the LIGO and Virgo detectors captured the gravitational wave signal from 2 merging neutron stars and simultaneously detected the optical and gamma-ray flash from the explosion. That merger produced an amount of gold roughly equal to several Earth masses. Every gold atom on this planet was produced in an event like that. The Milky Way, our galaxy, is a barred spiral galaxy about 100,000 light-years across and containing somewhere between 100 billion and 400 billion stars. Our solar system sits in one of the spiral arms about 26,000 light-years from the center. At the center sits Sagittarius A, a supermassive black hole with a mass of about 4 million suns. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, resolving its shadow against the glowing gas around it. Most large galaxies host a supermassive black hole at their center, ranging from millions to billions of solar masses. How these giants formed is an active area of research. Some may have grown from the mergers of many stellar mass black holes. Some may have formed from the direct collapse of enormous gas clouds in the early universe. The universe is also expanding, and that expansion is accelerating. In 1929, Edwin Hubble showed that distant galaxies are moving away from us, and that farther galaxies are receding faster. The universe is not static. It is expanding in every direction simultaneously. In 1998, 2 independent research teams studying distant supernovae found something unexpected. The expansion is speeding up. Something is pushing the universe apart faster and faster over time. That something is called dark energy. Dark energy makes up roughly 68% of the total energy content of the universe. We have no confirmed explanation for what it is. The simplest candidate is a property of space itself, a constant energy density that does not dilute as the universe expands. As the universe grows larger, more space is created, which contains more dark energy, which drives further expansion. Dark energy was first proposed as a way to explain the accelerating expansion, and every subsequent measurement has confirmed that it is real and dominant. The discovery of accelerating expansion in 1998 earned Saul Perlmutter, Brian Schmidt, and Adam Rice the 2011 Nobel Prize in Physics. Every subsequent measurement of the cosmic expansion rate, from supernovae distances to the large-scale distribution of galaxies to the CMB, confirms acceleration. Something is driving the universe apart faster over time, and it constitutes about 68% of all the energy in existence. The long-term fate of the universe depends on dark energy's behavior, which we do not fully understand. In the most likely scenario, the universe continues expanding forever. Over the next few trillion years, star formation slows as galaxies consume their gas supplies. The last red dwarf stars burn out around 100 trillion years from now. For an incomprehensibly long time after that, the universe is cold and dark, populated only by white dwarfs, neutron stars, black holes, and the occasional leftover planet drifting through empty space. Over even longer timescales, quantum processes gradually dissolve even the matter that remains. Protons may decay. White dwarfs and neutron stars eventually evaporate through quantum tunneling processes over timescales with more zeros than there are atoms in a visible universe. Finally, even the black holes go. Hawking radiation causes them to lose mass and evaporate over timescales, ranging from 10 to the 67 years for stellar mass black holes to 10 to the 100 years for supermassive ones. When the last black hole evaporates, nothing remains but a sparse, cold sea of photons and neutrinos, diffusing forever through an ever-expanding void. The numbers involved are almost beyond language. The Sun has about 5 billion years left. The last red dwarf stars die around 10 to the 14th years from now, roughly 10 trillion years. Complex organic molecules break down within 10 to the 30th years. The last stellar remnants disappear around 10 to the 40th years. Supermassive black holes finally evaporate around 10 to the 100th years, a number called Google, which is where the company Google got its name from, because the founders wanted to convey the scale of information they were indexing. This is the heat death of the universe, maximum entropy. No gradients, no structure, no processes of any kind, just an eternal, cooling, expanding nothing. Between the Big Bang and the heat death, there is a brief period in the middle where matter forms, ignites, makes stars, makes planets, makes life, looks up and asks questions, and then fades. That brief window includes everything that has ever existed. We are in it right now. And now you know the full story, from nothing to everything, all of astronomy in 20 minutes. The universe took 13.8 billion years to get to this point. You made it in 20 minutes. Proportionally, that is even more impressive.